Following lecture will cover Chapter 14, dealing with infrared spectroscopy, sections 1 through 4. So when we deal with organic structures, we need to be able to identify the exact structure and structural features of those molecules. So how do we know? How do we know how the atoms are connected? Whether we're dealing with single, double, or triple bonds. How do we know what functional groups are present? And you haven't done this yet, but chapter 5, we're going to learn about stereoisomerisms. So how do we know a specific stereoisomeric configuration? So we have to determine all of these things in organic chemistry if we want to understand the structure of a molecule. Spectroscopy simply involves the interaction between matter and light. And when I say light, I'm talking about electromagnetic radiation, everything from radio waves all the way to gamma radiation. From Chem 1, you should be familiar with the properties of light, which include wavelength, frequency, and energy. And you should know that wavelength is inversely proportional to energy, while frequency is directly proportional to energy. The electromagnetic spectrum includes the range of possible frequencies of light. Our longest wavelength frequencies of light are microwaves, and there's actually radio waves further to the right, and gamma rays, which are your highest energy. Where microwaves are the lowest energy. And the region of the spectrum that our eyes are able to see is this tiny sliver called the visible spectrum, which ranges from approximately 400 nanometers to approximately 700 nanometers. Different regions of the electromagnetic spectrum are used to tell us different information about a molecular structure. So, simply put, different forms of electromagnetic energy interact with matter differently and give us different types of information. For example, radio waves can be used in nuclear magnetic resonance, NMR, and this is basically the same thing as MRI. In the healthcare industry, we just don't call it nuclear magnetic resonance in a hospital setting. But this gives us the specific arrangements of carbon and hydrogen atoms in a compound. Infrared radiation is used in IR spectroscopy, which is going to be our focus of this chapter. And this gives us information on the functional groups present in a compound. And UV vis can be used in UV vis spectroscopy. And this gives us lots of information. Not only does it give us any conjugated pi systems, but groups that are chromophoric, meaning they will absorb light. We can use those molecules to tell us about solution concentrations. We can monitor reactions. There's a lot of things you can do with UV vis spectroscopy. So with IR, which is our focus, IR spectroscopy, infrared light causes molecular vibrations. And when I say molecular vibrations, bonds can stretch. That's one form of vibration. Bonds can bend, like scissoring, and bonds can twist. So when we say infrared causes vibrations, we're essentially talking about that type of radiation causing the bonds to bend or stretch in a number of ways. So we're going to be focused on stretching frequencies, they're the most useful in identifying functional groups. All right, so all this slide is telling you is that different bonds require a different amount of energy to cause the vibration. So a carbon-hydrogen bond requires a larger amount of energy than a carbon-oxygen bond for a particular vibration. That's it. The IR frequencies absorbed tell us about the bending and stretching of those bonds, and from a spectrum, we can infer the functional groups that are present in a molecule. So this is what a IR spectrum looks like. It's a plot of transmittance on your y-axis, which is a function of frequency. And on the x-axis, that's wave number. And the peaks are called absorption bands. The units of frequency, the units of IR are frequency, and we use wave numbers. So these values range from 400 to 4,000 centimeters on our x-axis. And when we talk about a particular peak due to a functional group or bond, we're going to be discussing three very important characteristics: where it lies on the x-axis, the intensity of that peak, and the shape of the peak. So these are super important, and we're going to break this chapter into our understanding of where it lies on the x-axis. What does that tell us? What does the intensity of the peak tell us? And what does the shape of the peak tell us? And remember, this is all about determining what functional groups are present in a molecule. So in the end, what you're going to be able to do is look at a spectrum and identify the functional groups present in a molecule. And there are very characteristic wave number, intensities, and shapes for particular functional groups. So let's discuss some of the background as to how this bending and stretching occurs. So infrared radiation is largely thermal energy, and it causes stronger vibrations in covalent bonds, and we can think of them as springs held together by two masses. So at equilibrium, we have a particular bond length, and you apply energy or a specific frequency, and that specific frequency will cause a stretch or compression. Hooke's law describes the elasticity of a spring. And although we're not going to be plugging anything into this equation or applying anything from this equation, it does tell us some important things. It applies in the sense that the stronger bonds will absorb IR radiation at a higher frequency. So some factors that affect the wave number, or where it lies on the x-axis, are your bond strength and the mass of the atoms attached. So what we expect to see based on this equation is that the frequency or wave number will increase with increasing bond strength and decreasing mass of the atoms attached. Bond strength is our numerator, and the mass is the denominator. All right, so we can begin by looking at where on this x-axis certain types of bonds will give us a peak. We're able to see that single bonds have a very low wave number. Double bonds are a little higher than triple bonds. Remember, bond strength relative to single, double, and triple. Triple bonds are the strongest, single bonds are the weakest. So that was the first factor that affects where it ends up on the x-axis. The second factor was the mass. Remember, the wave number will increase with increased bond strength and a decreased mass. So let's try to understand why anything bonded to hydrogen has such a high wave number. Well, hydrogen has the smallest mass. It's a very light atom. So based on the equation from the previous slide, we established this relationship, and we can understand why single bonds have the lowest frequency, then double, then triple, and then finally why anything bonded to a hydrogen will have such a high wave number because of hydrogen's small mass. The region above 1500 is our diagnostic region. Anything below that is called the fingerprint region, and it's extremely difficult to analyze. So, 1500, who cares? We're not going to be using the fingerprint region for functional group identification. We're going to be focused on the diagnostic region, and we're going to understand wave number, intensity, and shape of a peak, and how it gives us information on the functional groups present. Let's focus on the wave number here for different types of covalent bonds. So we have, let's take 2-butanol, 2-propanol, these structures. They're virtually indistinguishable because they have the exact same types of bonds. The connectivity is different. We've got an additional carbon-carbon bond. We've got more carbon-hydrogen bonds here. However, the types of bonds are the same. So when things are very similar, they're hard to distinguish on the IR. However, when we can distinguish differences, such as the hybridization state of a particular carbon atom, we can see peaks in different places. So let's compare the wave number, or the position on the x-axis, where we find different hybridized carbon-hydrogen bonds. So the higher the S character, like sp has a higher S character than sp3, the stronger the CH bond, so the higher the stretching frequency will be. So that's why down at the, we have our spectrum, okay, so if we're at, let's say, 3500 and 2900, we might see a peak for sp3 here, one for sp2 here, and then our sp will be here. But we'll look at plenty of examples. So if we're looking for sp, sp2, and sp3, we can look at the following examples. Everything here in this region, these are your alkane CH stretching frequencies. They're low. And the reason they're larger than the alkene peaks is because most molecules have a lot of carbon-hydrogen bonds. Our carbon-hydrogen bond that involves an sp2 hybridized carbon, we're going to have that peak a little bit higher because that's a stronger bond with more S character in the hybrid orbital. And if we move to our carbon-hydrogen bond, in which our carbon is sp hybridized, right, that has the most s character, and it will be even higher in wave number. Some alkenes could give IR spectra without any signals above 3000. So the only signals we were seeing was when we had a carbon to a hydrogen. Well, if we don't have any hydrogens attached, then you're not going to see that peak there. So we're going to be looking for the presence of alkenes and alkynes in more than one place. Those that have a hydrogen we'll see down at the far left end of the spectrum. But we're also going to be looking for alkenes and alkynes more towards the center of our spectrum. We just talked about the type of bond and where we'll see peaks on the x-axis. Now let's take a look at how resonance affects the wave number or the position on the x-axis. So resonance will typically lower the wave number or lower the frequency. For example, if we look at a ketone, which only has one resonance structure, versus a conjugated ketone, so you could push the arrows there, and you could also push a second set of arrows there. You could have 3 resonance structures for a conjugated ketone versus 2 resonance structures for a regular ketone. And the conjugation stabilizes, remember the conjugation stabilizes the charge and spreads that charge out over more atoms. In this case, we're spreading the electron density from the pi bonds out over multiple atoms. So here are our 2 resonance structures. For the ketone, we have the delocalization of the p electrons in our pi bond versus a conjugated ketone, which has those 3 resonance structures. And we see that resonance or delocalization of the pi electrons lowers the stretching frequency. Any conjugated carbonyl will have a lower stretching frequency, so that is the key. We just saw the example with ketones, and the same will go for esters. So we have a regular ester versus a conjugated ester. So anytime you see a carbonyl, single bond, and then a double bond on the next carbon-carbon, it will be conjugated, alternating single and double bonds. So we're looking for conjugated system, and we need to know that it will lower the stretching frequency. There's no reason to memorize all of these exact values. Just know that it will lower the frequency. And, we do want to have a relative idea that ketones are, in general, a regular ketone will be a little bit lower than an ester. However, all of the values will be slightly different depending on what's attached. So knowing the relative positions is what's important here. All right, so let's take a look at the following example where we want to rank the highlighted bonds in terms of their increasing wave number. So where on the x-axis will they lie? So pause the video and go ahead and give this one a shot and when you come back, I'll give you the answers. All right. Hopefully we're able to give this a try. And we see that the CH should be the highest. That's above 3,000. Then we have our carbon-carbon triple bond. That'll be next. And finally, the lowest wave number will be our carbon-carbon double bond. Remember, the reason the CH bond has such a high wave number past 3,000 is because it has such a small mass. For our next example, let's look at whether or not we'd expect to see a signal to the left of 3,000. Remember, everything to the left of 3,000 will be something bonded to hydrogen, carbon bonded to a hydrogen. And particularly a sp2 or sp hybridized carbon. So around 2,900 was the sp3 carbon-hydrogen bond. So let's not worry about that. So what we're looking for are the presence of any kind of sp2 or an sp hybridized carbon-hydrogen bond. So you can pause the video and give this one a try. When you come back, we'll look at the answers. Okay, so in our first example, A, we will see the peak to the left of 3,000 because we have an sp2 hybridized carbon attached to a hydrogen. Example B, there are no sp2 or sp hybridized carbons attached to a hydrogen. See that carbon, we have 4 carbons attached to our alkene. And in the last example, we have a sp hybridized carbon attached to a hydrogen. So we will see a bond to the left of 3,000. In the next example, identify which carbonyl group will exhibit a signal at a lower wave number. So if you recall, we're looking for a conjugated carbonyl alternating single and double bonds. And if you see a conjugated carbonyl, it will exhibit a signal lower than the regular carbonyl compound. So pause the video, give it a shot, and when you come back, I'll give you the answer. Okay, in our first example A, we have a conjugated system, a alternating single and double bond. So this will be the lower wave number. In example B, this carbonyl is conjugated, alternating single and double bond. So that is the carbonyl that will have the lower wave number. And for the last one, we have no conjugation. However, we have a ketone versus an ester. Now we just want to look at the relative positions. Ketones are always a little bit lower than esters. Now that we understand the wave number analysis, like where on the x-axis our peaks will be based on conjugation, based on bond type, based on hybridization, we're now going to look at the intensity of a peak. All right. So, for example, we have a very intense peak, which is a strong signal, versus a very weak signal. So what affects the strength of our signal? What affects the intensity? On polarity is the greatest influencer of the intensity. So the greater the bond polarity, the stronger the I of our signal. That is the key here. For example, look at the carbon-oxygen double bond versus the carbon-carbon double bond. We can see that our carbon-oxygen double bond, the carbonyl, is an extremely intense peak versus a carbon-carbon double bond is a much weaker signal. So if a bond is completely symmetrical, we won't observe any signal. So you'd expect to see a carbon-carbon double bond here, but this is completely symmetrical. There's no dipole moment here. There's basically all the stretching frequencies will cancel each other out. Stronger signals are also observed when we have multiple bonds of the same type. For example, the CH bond is not polar. However, when we have dozens sometimes of CH bonds, we're going to see intense signals because there's so many of them. So if you increase the number of a particular type of bond, we generally observe an increase in the intensity of that signal. All right, in example 14.5, let's determine which carbon-carbon bond will produce the stronger signal based on the factors that influence the intensity of that signal. So if we look at our carbon-carbon bond here, and we want to determine which one will give us a more intense signal, if you recall, the polarity of the bond will influence the intensity. So our second molecule here has a net dipole moment in the direction of the chlorine atom, and this will produce a much stronger signal compared to the nonpolar molecule on the left.